Problem 2501. Longest square streak in an array. This drawing is unrelated, but look at that. I'm really sick today, man. Okay, so you're given an integer array nums. A subsequence of nums is called a square streak if the length of the subsequence is at least 2, and after sorting the subsequence, each element except the first element is the square of the previous element number. Return the length of the longest square streak in nums, or return -1 if there is no square streak. Okay, a subsequence of an array can be derived from another array, deleting some or no elements without changing the order of the remaining elements. Okay, so we choose a subsequence 462. Okay, because 2 squared is 4, 4 squared is 16. Right, so as long as the subsequent element is a square of the previous element, you have a subsequence. But what's strange about this is that it doesn't have to be in order, right? Because it can go 2 to 4 to 16, just as long as each element has its corresponding element, which is the next number in the square kind of pattern. So that's a little interesting. So if we look at 2, there is none, right? Because 2 squared 4, there's nothing. 3 squared 9, there's nothing. 5 squared 25, there's nothing. 6 squared 36, there's nothing. 7 squared 49, there's nothing. So there's no such next number. So this problem is interesting. Let's look at example 1. Now, this problem has a very kind of intuitive, I think, dynamic programming approach, right? So let's look at this. So we have 4. I'm going to draw these systems as nodes. 3, 6, 16, 8, 2. Okay. All right. So when we look at each element, we want to make a decision about which other element it could be the subsequent number for, right? Like 4 can attach to 2, right? But 4 can only attach with things that are less than it, right? Like something leading into 4 has to be less than 4, right? So before we process 4, we need to first process 2, right? That's the only way we'll know that 2 exists. That's a better way of explaining that. The issue is like, what I basically want to create is a system where I know everything that goes before other things, right? Like 4 goes to 16, 3 doesn't go to anything, 6 doesn't go to anything, 8 doesn't go to anything, right? So I want to be able to determine this path, right? From 2 to 4, from 4 to 16. Now, in order to know that 2 goes into 4, when I look at 4, I have to already know that 2 exists, right? Because when you solve this problem, right, if you solve things one at a time, you can imagine, okay, I'm just looking at 4 first. So how do I know that there's a 2? I would have to process the whole array to find the 2 to attach to the 4. So the problem is since these thing doesn't have to be in order, right, there's this sorting aspect where in order to know what goes into 4, I have to know what comes before 4 in this array. So if I just filter this, kind of saying, before I look at a number, look at all the numbers less than it. That way I'll know if there's a number that is the square root of the current number that I'm looking at, right? Because the square root of a number is the same as the square of the number that goes into it, right? The square of 2 is 4. The square root of 4 is 2. So before I look at 4, I need to look at everything less than 4 to know if there's a number, if there's the square root of 4 in the system that I can attach 4 to, if that makes some sense, okay? So what I'm basically saying is what we should do first, before we process this system, is sort it. So if we sort this, we get 2, 3, 4, 6, 8, 16. Okay? So now when I look at 2, I know 2 is the minimum number. And since 2 is the minimum number, there's nothing, the square root of 2 can't exist in the system. Now I look at 3, I can look at everything less than 3, right? And I can just filter and say, okay, everything to the left of me can go into me. Everything to the left of me is a candidate, right? So is the square root of me to the left of me? No. Then I look at 4. I just know to look at everything to my left of me. And when I look at 4, I can say, okay, well, the square root of 4, is this a square root of 4? Yes. So that means I can attach a link from here to here, right, from 2 to 4. I look at 6, I say, is 2 the square root of 6? No. Is 3 the square root of 6? No. Is 4 the square root of 6? No. Okay, I look at 8, I say, is 2 the square root of 8? No. Is 3 the square root of 8? No. Is 4 the square root of 8? No. 6 the square root of 8? No. I look at 16, is 2 the square root of 16? No. Is 3 the square root of 16? No. Is 4 the square root of 16? Yes. So then I can create this link, and then I can just find the longest path in this graph, or just, you know, better yet, I could just say, you know, I could just do a dynamic programming approach where, you know, I consider all of these things length 1, and then when I find a neighbor that goes into me, I make this link 2, right? This is link 1, this is link 1. When I add 16, I say, okay, there's 4, and 4 is link 2, so I'll add that to me, and that'll be link 3. And then the answer is just the maximum such path. So this would be n squared, right? So you do n log n to sort the system, and then n squared operations, because for each node, you look at all the previous nodes to see if you can find the square root of you in the system. But to speed this up even further, well, we don't really need to look at everything that comes before us. We just need to check. How can we check efficiently that the square root of us comes before us? Right? We know if the square root existed, it will come before us because we've sorted the system, right? So we know that's a fact, but we don't need to look at every single node, right? Can we efficiently check if something comes before us? And that's where we're going to introduce this idea of using a... I don't know what just happened. Did this thing bust or something? The operation could not be completed as thought. What is going on? Yeah, I don't know what's happening right now. It's very strange. Come on. That's so weird, man. I'll just continue. So this problem is then very similar to two-sum, right? Because when you do two-sum, the idea is you have two numbers that match together to get you to a target, right? So in this case, there's kind of a matching number for any number, right? If I have 16, the matching number is the square root of 16, which is 4, right? So for any number, there is a matching number that exists that we want to consider as the previous element in this subsequence, right? So there's a previous element for a number, and that previous element is the square root of the number, right? So when we look at, I guess, when we look at the case of, you know, two-sum, we solve that problem by using a hash table, right? A hash table will hold information about the previous numbers. That way I can efficiently check previous numbers instead of having to look through the whole system, right? So I look at a number and I say, okay, does that previous number exist in the hash set of all the numbers I've processed so far? If so, then I can just take that number, the number of subsequences that lead up to that number, and then add it to the current number. I don't know what's going on with this tablet thing. It's weird. I'll have to debug that later. So let's just go ahead and finish this problem by doing the code. So first thing we'll do is we'll sort the system, right? Because that'll let us easily filter for any number of the numbers that come before it. All right, and then what we'll do is we'll look at each. We'll have a hash table D. We'll make it a default dict. So for every number, right? So we'll look at each num. The value of that num, we'll divide it by 1, so it's a float. Instead of an integer. Right, because we're going to be taking the square root of something, so the square root of it is going to return it as a float. Right, with point precision or whatever. So d of num is 1, right? It's always at least 1. Plus, well, does the square root of that number exist in the numbers that we've seen so far, right? Because every time we see a number, this will get updated. And then it'll get updated to the link of the longest subsequence up to this point. So how do you take the square root of something? So you take that, and then you do 2.5. Okay. And then at the end, we return the max of the values of d, right? But... right, it has to be at least length 2, right? So we could look at each value for value in d dot values. If the value is greater than 1, right? And then if there is no such thing, right, if there is no such subsequence, we just return -1 as our default value. And we'll just make this shorter. 3-line solution, the perfect dynamic programming approach. All right, cool. Whoa. This is probably small because I'm adding another whole layer of complexity for this. So let's try that. Make it a generator object or whatever. Nope, that doesn't change anything. I don't know what's going on with that. Okay, so let's see. So what's the runtime and space complexity? Okay, run and space complexity. So let's say n equals length of nums. All right, so for time, we create a default dict. We have to sort this array, right? So that's going to take big O of n log n time to sort. And then we have to look at each element, which is going to take n time. So that's n log n plus n, right? It's going to get shadowed by n log n. So sorting this thing is really what's going to take the longest amount of time. But n log n, that's good. We could maybe get it in n time, depending on if we did like a radix sort, right? Like a bucket sort. No, because the numbers are too big, right? So that's not going to help us. Okay. All right, and then for space, well, we have to create this default dict that we're going to populate with each number. So that's big O of n. All right, guys. Thank you.